Well, I think what we'll do is we'll start. I think if it's all right with you, what we'll do is we'll go in alphabetic order. And the first presentation I have is from Alfredo Flores, who isn't here, but I'm going to play his thing for us anyway, so we can see what he has to say for himself. And if you recall, he's doing the leaf blower, and this is the homework assignment on societal impact. And so he's going to tell us about the societal impact of his leaf blower's active noise suppression system. I can just imagine what that might be, but I'd like to hear it from him. So, without further ado,
My name is Alfredo Flores, and today I am going to talk about the societal impact of my design. My design is about a quiet leaf blower, but the applications are endless. My design has a number of great applications that are going to improve our life. Hearing loss. People working near aircrafts or in noisy factories are exposed to hearing loss. My design is going to decrease the number of people that are affected with this problem. The use of hearing aids and hearing operations are going to decrease. People exposed to high noise levels present mental health problems, chronic sleep disorders, cardiovascular problems, and increasing stress. One of my goals with my design is make an impact in our society. Efficiency. Efficiency in automotive industry. A better exhaust system will increase horsepower and improve gas mileage. My design allows exhaust gases to escape more efficiently and free up the engine to produce wheel driving power. Vibration. Noise cancellation eliminates vibration. My design could eliminate some health problems caused by vibration. These problems start as a pain, but they might be developed into injury or disease. Vibration could introduce changes in tendons, muscles, bones, and joints. Even the nervous system could be affected. Vibration may become destructive. Components that are vibrating have loose bearings or are loosely attached to its mounts. Vibration can produce machinery to consume excessive amount of energy and reduce product quality. Thank you.
okay, so what did we think of this one? Societal impact. There was something in here that bothered me. It's a leaf blower, right? Why is he talking about the automotive industry and horsepower? Gas mileage in a leaf blower. Is it inconsistent with the product? As claimed, it's a leaf blower, right? We don't drive it. Or is he suggesting that because this might have application in the automotive industry, that might be another area where it has impact? It's not clear. I can sort of see where people around you will feel better about not having all of this noise, and even the vibration reduction could help you quite a bit, even if you've got hearing protection. So I can see where that's a great benefit. Quiet leaf blower. Anything else? Societal impact? No? Nothing? We're good? Alright. Let's see. What do we got here? Sarisha? It's time for dry ice.
I'm going to present how I mean my thesis proposal is going to affect this society. Because of using dry ice superconducting motors at driest temperature, we can reduce the resistive losses in rotor that we are using in motors. And we are using superconducting magnets, so we can increase the efficiency of the motor at driest temperatures compared to permanent magnet motors. So driest temperatures at driest temperatures we can decrease the loss, like cost of the product, because the problems are like cooling cooling methods that we use in motors we can decrease at driest temperature. Cooling methods that we use in motors, those cost more for liquid nitrogen temperatures, because like for using temperature cooling there are different methods. At driest temperatures we can decrease that seven times cheaper compared to liquid nitrogen temperatures. Superconducting magnetic motors are mainly like if we use superconducting magnets we can decrease the size of the motor. That will impact society more than everything else. Like we can decrease the cost, we can increase the efficiency and everything, but the more impact of superconducting elements in motor decrease the size of the motor, so it benefits the society. And using superconducting motors at driest temperatures we can increase the stability of the motor, because we use transient we use at small load angles at transient temperatures. So I guess it's going to impact society in a good manner using superconducting motors at driest temperatures.
Okay, so here's the problem that I was having. I like the idea of a high temperature superconducting motor, but I want to know what I can do to make money with it. So you need to sell the product. So if you told me, look, I can make a 100 watt motor that has 10 times the power using super cool high temperature dry ice than a normal motor, then that speaks to me as
Innovative.
a superior, an intrinsically superior thing. Right now you're telling me, oh, for 100 watts I can have a 10 horsepower motor, whereas if I was working with normal motors I would only get a quarter of a watt. And if I needed to run something like a dryer, which needs a motor, I could do the dryer with a tenth the power using my dry ice system. Although the dryer is hot
Yeah.
and the motor is cold.
Yeah, but like I'm thinking we have still 16.5 kilowatt superconducting motor at liquid nitrogen temperatures. So if we do 16 kilowatts power motor at driest temperature, so it's gonna be like impact the
So
society.
if you go back and you say 7 or 10 times, what are we comparing? Is this difference in temperature?
No,
7 times?
it's a cheaper cost.
Why is it cheaper?
The cooling methods for driest temperatures are different for liquid nitrogen temperatures.
So dry ice is what, minus 77?
No, it's 195 K. So
Well, you have to add
273.
right? So how much is it in Celsius?
It's 195. I'm poor at math.
I'm thinking
Six.
that liquid nitrogen is 100 degrees colder than
Dry
dry
ice.
ice.
Yeah.
Whether it's Celsius or Kelvin, it doesn't matter.
Right.
It's still
Yes.
100 degrees.
100 degrees different.
I thought dry ice was something like minus 71 or minus 77, something like this.
Yeah.
So I can see why it would be cheaper, but I don't understand where 2 to 7 times comes from.
For superconducting magnetic materials, the cooling methods are cheaper compared. By looking at the cooling methods that we use for superconducting magnets, it's 7 times cheaper generally for liquid compared to liquid.
So let me get this straight. I understand it's 100 degrees warmer. What I don't understand is why it's 7 times cheaper.
It's not like exactly 7 times cheaper. It's around like it's cheaper compared to liquid nitrogen temperatures.
Well, I can understand why it's cheaper than liquid nitrogen because it's 100 degrees warmer. So it's got to be easier to cool down to minus 70 than it is to cool down to minus 170. Why not? The 2 to 7 times just throws me a little bit. The question of exactly what it is I'm going to get for this temperature is still open. Are dry ice motors just as efficient as liquid nitrogen motors?
If in case of efficiency, like we are using superconducting magnets, right? In both either dry ice or the liquid nitrogen motors. I mean, like temperature at liquid nitrogen. So, in case of efficiency, we can have same efficiency, but we are increasing the temperature that we are.
So it's the same efficiency.
Yeah.
Dry ice motors are just as efficient as nitrogen.
Nitrogen motors, but we can have that at dry ice temperatures.
But at dry ice
Temperatures.
So they are intrinsically better. Okay. Sporty. Okay.
In this one, I'll tell you about the societal impact. The first one, this is how people will know about our project. First, we have to tell them about our project. How will we reach them? First, we can use any social platforms so that we can tell them that we are doing, like, we have this idea, and then we have to post updates, and then so that when they respond to our updates, you can just reply them, and then in this way people will know about our project, that our idea is existing, and then they'll ask us about the questions like how is this useful for us, and then what are the how is it is useful for society. Then the first thing, in my project, it is helpful to reduce the electricity bills, and they can know how much each electric device is consuming. And then when we use this one in the smart grid, it is helpful in reducing the blackouts. And then finally with this we can reduce like we can save the money, and we can even save power, so that it will be useful in future, like power distribution will be exact, and then power is, yeah, and we can use power efficiently, so that power is useful in the future too. That's it.
So your first slide didn't really talk about societal impact. That's
No,
marketing.
I just wanted to tell how people will know about our project, like they.
Yeah, but you see, that marketing is a whole other.
Yeah, I
presentation.
just okay.
Yeah, that marketing question is not
Yeah.
that's not the homework assignment.
The main thing is
go
the
to the
second
next
slide, but then I just wanted to tell how will people know about our project, so that they'll ask us the questions, right? How is this useful to the society? So I just mentioned it in the first slide. That's it.
So societal benefit
Yeah.
starts by saying you will tell people your idea it is useful.
Mhm.
But that's not, why is it useful? That's the real question.
Yeah.
So, so maybe it's not saying it's good. It's telling people the good things, right? You could say, tea is good, but maybe what you really should say is, tea helps because it has antioxidants and has,
Yeah, got it.
lubricates your throat and makes you live forever and whatever.
It
It
helps
makes
them
you
to
feel
save the
better.
money. Yeah, that is the main thing of this. That
Maybe there's something about listing the features that make this sell. Think about it as though you were talking to somebody who you wanted to sell to. You're the door-to-door smart grid salesman, right? Smart grid salesman? Oh no, not again. Yes, I'm here to sell you smart grid. Okay, I'll bite. Why do I need smart grid? It's useful. That's not good. You have to say it's useful because, right? This is going to save you money. This is going to
yeah,
be the thing that you need to hook up your iPhone to your outlet without
and then
having
we
a
can
short
find out the
circuit.
power exact. Yeah.
I show you my demonstration here. Look at the sample app, and boy, this is the best thing. You've seen this, and you're going to say, I got to get me some of that. You even have a mock-up in there that says, this is my product, and you should buy me. Um, I had a big discussion about this morning. Someone said you can't get into the toy business with a printed circuit board. And that's what I have. It's like this audio DSP thing. And I said,
Yeah.
geez, maybe we could use it to help children learn math and signal processing. What is that? Circuit board. You can't give a circuit board to children. This is not packaged. It doesn't look nice. You have to do a mock-up. You have to
Make
make
it in.
sellable.
Yeah.
It doesn't look like a product. So when I look at this, there's probably something that's there, but it's hard to get at. The same thing is true with the dry ice motor. I think there's something I could sell there. What it is, I don't know. If I walk up to knocking on the door, hello, dry ice motor salesman, right? And they say, well, what do I want that for? Well, look at this dry ice, and look at this liquid nitrogen at 100 degrees. What? Can I put the dry ice motor in my vacuum cleaner? Oh no, don't do that. Can I put the dry ice motor in my dryer? Oh no, it doesn't go there. Why do I want this? I have trouble selling your idea. I think it's a good idea, but it doesn't really sell itself. You have to sell it.
We need to know about where we are using dry ice.
What is the application? I love the idea of knowing this is what you want to do with it. This is the problem. I want a technological problem. I want a technological solution to the problem. And then my criterion is that if I use existing technology to go from the problem to the solution and it's not obvious, then I've made an innovative leap, and then I can make a very good claim, especially if you reduce your, I'll call it, principle of physics to an enabling device, right? You have to make it patentable and really a strong patent. I think you have to reduce it to practice. So what you've basically been pushing here is a principle of physics, that you can make motors with dry ice, and isn't this a wonderful thing? But I don't know that this motor is something I can put in my vacuum cleaner or in my dishwasher or my dryer. I think maybe this motor goes somewhere where I don't know. Maybe it goes up in a big wind turbine that has a generator. Maybe that's where it goes. Or maybe it goes in a power plant, for hydroelectrics. I don't know where it goes. Maybe it goes in a locomotive. Maybe that's where it goes. But if I don't have a specific solution, I don't have a product. So I think that you really have to think in terms of what's the product. This is coming close to a product. This is looking like something I could go and sell on Kickstarter. I might be able to sell a prototype on Kickstarter, and it's not looking like the kind of product that I need in my Dyson vacuum cleaner. It's looking more like an Edmund science project. So I need to know more about where this is being applied. You know, and so there's something here, but I'm not sure where is it going. You know, if it's an exploration into physics, then it becomes this really sort of interesting thing, but it's almost, you can't hack the physical phenomenon here. You need to apply it. So this is very important. Thank you. Who's up next? Let's see. George? The Maglev defense system. It's a defense system?
I think that might be it.
Oh, this is wonderful. That we can sell. We have to tell the generals.
That might be it.
This is great. You make a rail gun with your
A rail. Not quite. So I'll be talking today about the societal impact of my invention. So it will benefit society in several ways. First of all, it will make space travel much safer. The threat of asteroids and other ferromagnetic fragments will be reduced, meaning the way it works is it uses magnetic levitation to repel. It's assuming that many of these fragments, rock fragments in space, will have iron-containing cores. That's the way that's the only way it could work. And it could also, mankind could travel further in space to unexplored territory, for example, due to.
What will it do to the metal inside the spacecraft?
Well, the system itself is based on the outside. It will be made to withstand the impact of the Maglev system. And due to the increased safety, mankind could travel further in space to unexplored territory. And once again, this is a hypothetical. It's not necessarily will happen immediately. It will obviously take some time to develop these systems. All right, safety. Future exploration. It will have a major impact in the future of manned space travel. For example, a multi-millionaire, I think he's American. He's already funded a flight to Mars in 2018, and the system will this will only happen due to increased safety. In order for man to travel to a place like Mars, the safety, the bar of safety has to be already very high, and then the maglev system that I'm talking about will help increase the safety to get rid of the rock fragments that lie between Mars and Earth. The invention will especially be important if we are ever to travel beyond the orbit of Mars in our solar system because of the asteroid belt. Conclusion. Alright, so if my invention makes space travel safer and therefore more tenable, it will benefit humanity by allowing us to push the boundaries of space travel in and eventually beyond the solar system. Both commercial and recreational interests, such as mining on other planets or personal travel, my proposed system could eventually lead to that. Which is both these are our. I mean, in the future, when we run out of resources on Earth, these things could be my proposed system could help us achieve these goals, but not right away, obviously, and maybe and it's hypothetical is what I want to stress here, so it's not really a it's sort of more of a long-term goal than anything else. And are there any questions or concerns or any comments?
So, what kind of power requirement is
That is, to be honest with you, that's something I haven't considered yet. But
Is this practical?
this is, I mean, it's practical. It's sort of a hard question to answer because it's not really, it's not something you can do overnight, obviously. It's something that, I mean, that's,
Will
it's,
you finish your thesis in your lifetime?
I might have to switch to something else, to be honest with you, but this is, I was trying to be creative with my, approach. It's, I mean, it's not something that I might, it may not be achieved, but I was trying to be, I was,
Is the SpaceX guy going to invest in you? He's got all that PayPal money.
PayPal money. I don't think it's something that you will be able to buy over PayPal. I think it's more geared towards the space.
Well, the SpaceX guy,
Right.
he got his money from PayPal.
PayPal. Okay.
And so then he decided that he would get into the space business.
Right.
And so now he's launching for NASA. They paid him over $1 billion just to deliver stuff. To
Oh,
the
really?
space station.
I've never heard of him before.
Oh yeah.
Oh.
I thought that's who you meant.
Well, someone like that. I mean, it's.
He could be your customer.
Yeah, I obviously haven't come up with a price for this, but it's likely to be very expensive.
Oh, you should charge a lot.
Yeah.
It's going to cost a ton.
Probably. Yeah. I don't
How
know.
much is all this going to cost?
I mean, probably over several $1 million.
And when will we be able to do our first prototype?
That's also something that I haven't yet considered. But these are the benefits that could result if this were to become successful. If mankind, that's why I put an if at the because it's, there are a lot of things that have to go right in order for this to but I was interested in using the maglev system because that was it's been used in like trains and one of the major benefits of it is the fact that it's, there's very little friction. But I wanted to use it in a new and creative way.
Can you use dry ice motors for maglev?
No.
Sorry.
No. But
All right, thank you.
any other comments or questions? Or
I think that if it worked with dry ice, then
if
it
we were
would
to
be
use
very
dry
good.
ice, but it's been used in space, so it's already cool.
Oh yes, it's already. Your motor will run in space. Oh, space is very cold. But when the sun hits it, it'll be hot.
Correct, but it will use the when it's not, I mean, I would have to consider if it was actually to be used in space, then yes, it would have to be cool. It all got cool.
So now we're going to see the societal impact of Witricity. Raul, you're up.
Good afternoon, everyone. Today I am going to discuss the societal impact of the Witricity concept. So before I go to the societal impact, I would like to give a clear view about what the Witricity gives to the society. So basically it gives two things. It gives a direct wireless power, and it's the same thing of the, like what the first thing explains. The second thing is the automatic wireless charging. So with the direct wireless power, our devices like the cell phones or any mobile devices can work without a battery when they are in the range of the electricity power. So when they are in the range of the wireless power. And it's coming to the automatic wireless charging. Um, we don't have to plug in the wires every time our battery gets dead. So because there is no, so the battery keeps on charging itself whenever it gets discharged. So um, it's like charging automatically. We don't have to mm, plug in or do any external things to power up the batteries
Why do you need batteries?
for the device to be running.
Well, can't it get the power wirelessly?
Yes.
So why does it need batteries?
No, no,
It's getting
even
power from the wireless.
yes.
So batteries are not needed. It's not
Yeah, we don't need batteries anymore.
right.
But in case, if for example we are using a mobile phone, so when you come into your home, it gets charged, and you leave when you leave the home. So when you are out of the range of the electricity, the wireless power,
But
then
I thought you were doing Arduino.
yes.
So Arduino doesn't care about wireless phones.
No, with your suggestions, I changed it not just for the Arduino, for the microcontrollers, for micro.
But I mean, what about if you just use a capacitor? Anything that stores power could be used, right?
Mm-hmm.
And the capacitor could be charged immediately.
Immediately, yes, but um, this like the concept. We are not using any external components. We are not attaching a capacitor or anything. It just charges automatically.
Well, isn't a rechargeable battery an external component?
Yes. So if the mobile phone has the rechargeable battery, when you come into the home, when you are in the range of the wireless power, it gets charged, and when you leave the home, it starts discharging
I
as
thought
the
it was a
usual.
microcontroller. You're back to
Yeah.
the mobile phone again.
No, I was just referring to the some particular thing. That's it. Not specifically for the. I was just trying to say what the wireless power gives to the public. So, um, so this impact on consumer electronics. So as you can see there are like um, any devices which use the microcontrollers like the phones, maybe the laptops or the controllers, game controllers, and I whenever these things come into the range of the wireless power, they get charged. We can use it, and the so so it's like the microcontroller is getting charged, and the device gets worked. So in the next point is we can also use it in our homes for the normal day-to-day day-to-day devices like the flat screen TVs, home theater accessories like the speakers, anything else which has a microcontroller in it. So it's basically powering up the device to work regarding the consumer electronics. And in the industries, so these days it's like um, the industries use a lot of wires to power up all the machines to get the machines get running. So using this concept, we can make the machines running by putting the wireless transfer in the area or in the zone where we want to power up the machines or anything else. So if it is like in a harsh environment like drilling underneath the ground, mining or anything else, so this would give a very good impact and usefulness for the people who are working underneath, and where the laying the wires is practically impossible. So apart from that, there are like other applications. We can use the direct wireless power connections and automatic wireless chargings for implantable medical devices. We can use even in the hospitals, or like like the surgeons who use small devices to for the operation or anything like that, and also even the robots can work with this electricity thing.
You liked it. I wish we had a more specific product in mind. It's very general. We can use it for this, we can use it for that.
Well, the concept is that kind of thing. Actually, we can use it anywhere where the electricity is used. So
But your claim for your invention is quite narrow.
yeah, of your suggestions, I was.
Initially it was just we're going to do the Arduino. That's the product. That's what we're going to do. And when we think about all the different things we can use it for,
No, but you suggested some suggestions. So with that, I got that not just for the I got a broader idea.
then we go to all microcontrollers.
All not just a single Arduino family or some specific kind of thing, but we are just going in a very broad way of.
Now your preferred embodiment could use batteries, but I think that if you have something that takes nanowatts, like the small Arduino, you could probably charge a supercapacitor a little bit,
Yes, for the yes.
or something like that.
If it is, for example, if it is an Arduino Mega AVR controller, which takes high power, yeah, which takes high power, then this concept is really useful. Yes.
Here, let me show you something. This is a lesson in microelectronics. Okay? This is a microchip that came from microchip. Microchip that came from microchip. This is the 8-pin on the side, 16-pin DIC. Okay? This here is the same thing, can I say it's shrunken? That's not quite English, but it's close. It's shrunken. See how shrunken it is? You can barely see the pins. Now I pass it around. When we go to something small like this, that's when we're talking nanowatts, and that's when you can use robots to assemble, almost for free. If I go to my guy in Milford with a 18-cent resistor, I say, please solder this into the board. He charges me 40 cents. He put in an 18-cent resistor, $4 to assemble a board. That's how much he charges me for my product. But if I go to pick-and-place machines that use solder paste to pick the little chips out of the tape and then put them straight onto the board, and then wave solder the whole thing, it's free. Assembly is free. So what happens now is you end up going to resistors, not that you can hold in your hand, but that are so small you can practically lose them in your eye. That's really tiny things. So when you look at this, and I'll pass it around. The difference between the two different chips is remarkable. I can't. It's so little I can't use it.
And also, it's like not just the microcontrollers using the normal electricity concept. I went through the fractal antenna concept, how it works.
Oh yes.
And
Fractal antennas, yeah.
yeah, so now my priority is like the electricity using fractal antennas and powering up the microcontrollers and whole very broad range of microcontrollers.
Hey Raul, did you ever upload? Oh, here we go. Let's not you. Ravi, you're up next, right? What do I got? 2 here. This the second one? Open. What's going on here? Okay.
So my idea is to find maximum power point of wind turbines. So let me say some basic things about wind turbines. We have very few wind power systems. The only reason is they have very poor efficiency. Let me show some figures why they have poor efficiency. By Betts law, the maximum efficiency a wind turbine can get is 59.08. It's some scientist who derived this, and the recent market available wind turbine has a maximum efficiency of only 40%, because we don't have the efficiency of the wind turbine is proportional to the wind speeds, where wind speeds are not constant or they are variable. So that's the reason they have very poor efficiency. In my idea, as an indirect social impact, it's like societal impact. It's like it improves the. It's a rough figure actually. 12% is a rough figure. Maybe 10 or 15. I'm not sure. I didn't simulate it yet. So I get the figure only when I simulate my idea. It improves the efficiency of the present turbines up to like 10 to 15%, which in turn generates more energy, and the other way it's like we'll get an energy at a low cost. That's what my idea is. And even every renewable energy source generation is have no negative impact on environment. So the other way, it has some societal impact, you can say. That's what my presentation is.
So how much money will you make with this?
Sure, I have no idea. I mean, I don't think I'll make it, because the only I can say is that this idea can promote installing more wind farms, because the only reason we have less wind farms and thing is that they have very poor efficiency.
But also the wind doesn't always blow.
Yeah.
So you have to store the energy, right?
Yeah.
This is the big criticism of sun and wind. When the sun goes down or the wind dies down, you have to make up for the difference with petrochemical products like natural gas
Yeah.
and natural gas-based power plants to fill in the gaps. So this is a big difference than from existing systems that can just be left on all the time.
Yeah.
So the real criticism, I think, of wind power is not so much its efficiency, but its consistency.
Yeah. I mean, as I said, it's the winds are varying, so no turbines, no wind turbine system have consistency or.
How could you store the power efficiently? In hydroelectric power plants, they pump the water uphill. That's the most common way to do it.
Yeah. I'm not actually. My idea doesn't store any.
You could use this to pump water uphill. You could have a big water tower and just, when there's extra power available, just pump the water up. And when you want to get the power out, the water falls down.
Okay, I'll think of it this idea.
Right? You can have big batteries, big liquid batteries. That's a new one. They have, when they have batteries, normally they're liquid plus metal, and then the metal plates degrade. But here in the new age, high temperature, pure liquid batteries can be used for industrial applications like this. Big batteries. Yes, terribly dense. So you still need a way to store power to make up for the fact that the wind will die down. But efficiency is good. You can sell efficiency. Can you patent this? It's not obvious?
I don't think so. It's not obvious.
Sounds like it's got good. Thank you. Are there any questions? Maybe if I could use this on maglev, but the trouble is there's no wind in space. Alright, so a funny thing is going to happen during our semester. Everything that we learned about the patent law becomes wrong. On March 16th, and today is, I think today is the 5th, isn't it? Yeah, soon, the America Invents Act has its central provisions go into effect. And so what that means is that for the first time in 200 years, we're going to have a major change in our patent system. This has caused a great deal of controversy. Some people find that this idea is unconstitutional. As a result, they have filed suit against the United States Patent and Trademark Office. They cite the Constitution, they cite the clauses in the articles, and they say you cannot just go around passing laws that violate the Constitution. Courts will rule on this. There is no question that this is actionable, that there is foundation, and people feel as though the entire act, in its entirety, should be prevented from being enacted. And that is to say, the court should grant an injunction against enforcing the America Invents Act in its entirety. That is what the lawsuit says. So the question of how the court will rule is still open. Nobody knows. We're basically learning about the America Invents Act under the assumption that it will become law on March 16th. The question of what the court will do about it, we don't know. There is uncertainty here and controversy. So why? Why do this? Well, apparently the rest of the world is on a first-to-file basis. And so the rest of the world says if you go to the patent office first, you get the patent. Whereas in this country, if you're not filing before March 16th, the person who invents first, but doesn't necessarily file, can get the patent. And you can prove in a court who came to the invention first by using documentation like an inventor's notebook. The inventor's notebook typically consists of a paper-bound copy of your notes with dates, typically with an inscription that says read and understood, and somebody signs it with a date, so that you can show in a court of law that you have priority, that you invented first. Another way you can show that you invented first might be to take what you've invented and file a document disclosure with the patent office. Some people say the poor man's patent is to take what you've done and mail it to yourself with certified mail to show that you have, in fact, created this at a specific time. That's a way to do it. Another way, of course, would be to simply file a provisional patent application, which is actually a much more compelling thing because then you're assigned a number and your patent is entered into what's called the file wrapper, and the file wrapper is made accessible to all patent examiners. So patent examiners can look at the file wrapper even if you can't. So there are a couple of things that are guaranteed in the Constitution. Article 8, Section 8 describes intellectual property, and what it does is it says that the Constitution protects inventors, not people who do their paperwork first, but inventors. So you have to not only be the first to file, but you have to be an actual inventor, which means you're the person who took the invention, I'll say, the leap, the inventive leap between the problem and the solution given the prior art. So this is one of those things where, you know, you have to make a decision. And I've had this discussion numerous times with inventors. I just had it yesterday, a very lengthy discussion. The fella asked me, should I patent? Have you patented? How much will it cost me? Basic questions. And my answer to him, and what I will tell you right off, is the decision whether or not to patent is always a business decision. You have to look at what the value of the patent will be in terms of your business. And if it's not worth it, if the patent costs more than you can possibly make, from the invention, don't patent. It's as simple as that. You can seek other means of protecting your invention. I'll give you an example. I opened up a device recently. It was a device that converted audio to USB. I was very interested to incorporate the device into my next Arduino Shield. I said, oh, let's see what kind of semiconductors they use in here. I think it's probably the Wolfson IC, which I've heard so much about. So I open it up, and what do I find? A black chunk of plastic. Right? How do I know what's in there? Well, the only way to know is to chisel away the plastic without damaging the electronics and to try and read off the top of what would be a very small integrated circuit. And you've seen how small they can be. It would be totally impossible for me to burrow through the plastic or dissolve it and try and find out what's in there by reverse engineering. So they've created a means of protecting their intellectual property by using a trade secret. By potting, using epoxies or plastics, by potting your electronics, you can protect its insides and protect it from reverse engineering. And reverse engineering, by the way, is not stealing. Reverse engineering is a respected form of engineering. It means looking at something and going, gee, I wonder how that works. How did they do that? And that happens all the time. You know, you look at something like this laser printer and you go, gee, that's a nice thing. I wonder how they did that. And you take it apart and you look at it and you analyze it and you figure it out. That's reverse engineering. Reverse engineering means taking a schematic diagram and coming back to a high-level problem specification, like a finite state machine diagram. Reverse engineering means looking at a set of gears and thinking, gee, I wonder what the gear ratio is for that little motor. And I look at that little motor and I think, gee, by putting in the right plastic gears, it makes it look like a big motor. You know, that's a very interesting idea because a lot of times you'll have very cheap servos acting like very big servos that just happen to run very slow. So there are all these different interesting things you can do to try and reverse engineer. But then you want to stop others from copying your stuff, so you create what are called these so-called trade secrets. Coca-Cola has a secret formula, right? They keep it locked in a safe. Only a few people have access. The secret formula for Coke. That is their sustainable competitive advantage. So as a result, they have a trade secret, which lasts indefinitely, right? Trade secrets do not expire like patents or copyrights. So in some sense, one could make a compelling argument that trade secrets are perhaps cheaper, longer lasting, maybe better for your business in terms of your expenses and the peace of mind that they can afford. So having internally protected, for example, Microsoft. Microsoft has an operating system. That product could represent a substantial fraction of Microsoft income. They do not give you the source code for their operating system. That's a trade secret. They don't have to copyright it, but they probably do. They don't have to patent it, but they probably do. But the real key is if you want the source code, you better work for Microsoft. Otherwise, they're not going to give it to you. So this is one of those trade secrets. Very important. Keeps the sustainable competitive advantage. Otherwise, what would happen? Somebody like me would come out with Doc Java Windows. And it would look just like and work just like Windows 7 or 8 or something. And everybody will want Doc Java Windows because Doc Java Windows are free and open source. And if you want support, you can pay me for my normal consulting rate of $350 an hour, not including travel. So I think that it's a very good idea for Doc Java Incorporated to compete with Microsoft until I meet up with their gang of lawyers, and then they come and bust my kneecaps, which I've grown quite fond of. So it turns out trade secrets they abound in industry, and they're much easier to keep than you might otherwise imagine. What about trademarks? That's another form of intellectual property. Coca-Cola has a very fancy trademark, right? It's not just I'll say the words Coca-Cola or the expression Coca-Cola, but it's also the script, that interesting script that makes it look like a Coca-Cola item. That trademark is also indefinite in terms of its life. You just renew it. You just pay more money. And then it says TM. So it's trademarked, it's registered, they use it in commerce. If you use it and you call your drink Coca-Cola and it looks like it's got a script Coca-Cola on it, boy, they're going to get you. And it's not going to matter if you're making it in Antarctica. They will find you. They'll send a team with their pickaxes and their knee-breaking stuff, and that'll be the end of you. So it turns out there are international laws that govern trademarks. There are international laws that govern copyrights and also patents. For trade secrets, there may be international laws too, but I'm not so familiar with them. In this country, it's very clear. You have to take reasonable precautions. If you have an employee who walks off with a trade secret, then you can effectively sue them. It's actionable. Of course, it may not help you, but there it is. Then when you go to file your provisional, you get a year. A year, it might be enough time for you to decide whether or not you have a market for your product. If it's not enough time, you may want to file another provisional, but not exactly offer the product for sale. For example, you might have a provisional patent on magnetic levitation defensive shields, but maybe you're not exactly sure how to reduce it to practice. So what you'll do is you'll mention the idea, but the actual implementation you keep to yourself, because the solution is where the inventive step comes in. And so then you turn around and say, aha, after a year, I really can't sell this yet. I'll file another provisional. You can still have priority, and you can improve the provisional, increase the claims, increase the details needed to reduce to practice. There's another problem, though. If you disclose all the details needed for making maglev, by virtue of disclosure, you have published. That publication is a positive barrier to patentability, unless you filed your provisional. At that point, you do have 1 year. So then, after you've disclosed during that year, you had better convert the provisional into a regular patent application. So then there are these different kinds of provisionals that you can file and different kinds of regular patent applications you can file. You can file a patent on a plant. Life can be patented. So this is quite controversial, but it's been done before. That means that if you're Monsanto and you have devised a new genetically modified organism, let's say corn, that can resist some kind of disease or insect, you can patent the seed. And then the insidious part of it is you can sell it to countries that may be relatively impoverished or may be hungry. And one of the things they'll find out about this insidious genetically modified organism is that it does not reproduce. It's, in some sense, sterile. And so what that means is while the seed will bear a plant that will bear fruit, the corn kernels do not allow for self-replication. So you can't take the corn kernels and make more corn. And this will be something that they may have deliberately engineered into the product so that you must continue to buy seed from them. They give themselves a sustainable competitive advantage. This is one of the things people object to about genetically modified organisms, aside from the fact that they introduce interesting genetic material into the food chain. There is another kind of patent we'll call the utility patent. That utility patent is the one engineers typically use. That's the one I would use if I was going to patent my Arduino shield. But suppose I had an idea that I would take the printed circuit board, which just looks like a printed circuit board, and said, this is not packaged right. So I go to an industrial designer, I figure out, I say to him, oh, could you make it look like a guitar? Well, batch PCB will mill out any shape I want. So it doesn't have to be a square circuit board. It could be round so it fits into Ryan's yo-yo. It's very important to Ryan that we convert his yo-yo into a smart yo-yo and then give it Bluetooth with Wetricity for charging so that he can proceed to yo-yo around and have Bluetooth communication to his computer. And so we think that smart yo-yos could sell for over $100. Isn't this exciting? It's not so much how much it costs us to make, it's what we can sell it for. That's what's important. So if we want to keep our nice profit margin, 40%, then we have to be able to make it for under $60. Oh, I think we could easily do that. Although professional yo-yos are quite expensive. And so this would be a utility patent. But if you make it so that it's, kind of looking like a guitar and fits inside of a plastic box, that design becomes a design patent. Suppose you said to me, well, I'm an architect and I want to design a building. You can patent a building design. You can patent a bridge design. And then you have a sustainable competitive advantage as an architect, getting your design patent in, giving it ornamental features. But if you said, there's something else about this bridge which makes it interesting. It's a central suspension bridge like the Q bridge. That's a utility patent because of its usefulness. So now you can get two kinds of patents on the same thing, both utility and design. And then you could turn around and say, and by the way, I have a way to pour the concrete that I'm not going to tell anybody because it's too hard to protect. But if you don't pour the concrete right, this bridge will fall down. Well, that you could make a trade secret. So now you've got your sustainable competitive advantage. You could say, I've got this interesting bridge. I've got a utility patent on the structure, the basic structure that you can see. I've got a utility patent on the design because this is how I want the bridge to look. I got a trade secret because of how I pour the concrete. And by the way, I've got a fancy name for this bridge. Right? I call it the no-fail bridge, whatever. And so the no-fail bridge name becomes nofailbridge.com. And nofailbridge.com is a registered trademark. And I do commerce under that. So now I got the trademark, the trade secret, I got the utility patent and the design patent. I've got everything but a plant patent. So this is a very interesting idea, right? You got all these different layers of intellectual property surrounding this bridge design. Then there was this thing that the universities were doing. They were engaging in research. Now, when universities engage in research, it's really very interesting because professors have to publish or perish. Professors want to do things like get tenure. So they're encouraged to give away their knowledge. But what they're really doing is they're giving away their intellectual property. So what they do is they create what's called a technology transfer office. And all faculty in most universities end up signing what's called an intellectual property agreement. They have such a thing here at Fairfield University. And what it says is your patents can have your name on them, you're the inventor, but you assign them to the university. And so then the university gives you some royalty based on the patent and can proceed to license out your design. So maybe your royalty is 30%, but the university is paying for filing all the patents. They go through the process of licensing the patent and effectively convert your I'll say your idea into something that's commercial. If you're not happy with that, then don't use university resources. So for example, me personally, when I do the Arduino Shield, I keep it off campus. And I don't hire students to do it. And if I wanted to hire students to do it, then I would say, okay, if we're going to use our resources here on campus, we have to take into account our intellectual property agreement. If students do it on their own and it's their idea, then it belongs to them. Students have their own intellectual property agreement. And if the idea is coming from a professor, that becomes very tricky business. So, you know, you have to be careful about that sort of stuff. If you're doing the research and it's federally funded, a lot of times what happens is the intellectual property belongs to the government. And so they get first dibs on the patent. So if you have an NSF, National Science Foundation funded research grant, the NSF gets first dibs on the patent, and the federal government does too. You know, so it could be the Department of Defense wants your stuff. It's maglev for defense, right? The defense shield, right, George? Yeah. So DoD would come in and they would take it. Say thank you very much. So universities have to grant licenses. They don't assign the patent. The government has an interest in the patent. They can take it. They have to share the income with the inventors, so that must mean the faculty. They use the residue income for research. That could mean overhead. And they grant non-exclusive licenses to the government. That means the government can come in. They can use it, but it's the case that others will be able to use it too, non-exclusive. And that's from 1980. Since then, the amount of funded research that has been converted into technology transfer has just blossomed at universities here in this country. So a change in law like this can have real impact. I'll give you an example. In 1980, Rensselaer Polytechnic Institute started an incubator for starting companies to help with technology transfer. During that period of time, they've had a number of home runs. One of the home runs was MapInfo that came out of the Rensselaer Science Technology Park. That sold for $450 million. That pays for an awful lot of years of research. That's big money. So they're creating wealth with this Bayh-Dole Act. So what we can do is we can effectively ask basic questions like, since, let's say, the year 2000, how many jobs have been lost in terms of manufacturing? And the answer could be something like 42,000 jobs, maybe more. And then the question is, okay, so then how do we increase the number of jobs in this country? And people are wondering about this very, very question because we have what they call a trade imbalance. Right? Trade imbalance means you're bringing in more goods and services than you're shipping out. And the trade imbalance in this country on a per year basis is about $752 billion with a B dollars. Right? So that may mean you're getting oil from the Middle East and bringing that in. You may be getting goods and services from China and bringing that in. You may be, reducing the total number of jobs in this country because you have a very high salary requirement for the jobs in this country. But at the same time, when you start to outsource very quickly to other places, like China, for example, what happens is the general salaries start to increase. So while salaries may have been under $1 when all of this started, let's say back in the 80s, now it's probably up to more like $6 an hour. So there's a big question about whether or not this shift in the marketplace of manufacturing will eventually equalize. As we'll say, the cost of manufacturing in this country declines because of efficiency and also because of, let's say, cheaper energy, maybe manufacturing will start to come back, but it'll have to be manufacturing that's very efficient. So then the question becomes, how do you bring those jobs back into this country? People still don't know. It can't just be our ability to invent. because in this state we are producing more patents per capita than in almost any other state. We're like fourth highest in the union. Yet the jobs continue to leave. So it can't just be patents and our ability to invent. But it might help. There's this thing about prior art which we've been talking about before, and when you're doing a readings course, it's so important to start to think in terms of doing some reading. So what I'd like to see, and I think it's very important that you do this, that there should be one major paper per week at least that you can look at. It's so important that you pick the right paper. It has to be relevant prior art, or maybe even the most relevant prior art that you look at. So when you start to think in terms of a readings course, it's very good to look at your prior art, and it can't just be patents. Prior art should be journal papers. It should be papers, let's say, that come from the IEEE. In the case of the Google Scholar, we've already seen how to do some of those paper ordering activities. Have people all tried to order stuff from Google Scholar? Have you tried that yet? Did I show you how to do it? I did, right? You should all start ordering your papers. You're going to need more than one. Those papers are going to be very important to you because you're going to have to write a paragraph or two about each paper that you've written. So whenever you've seen a paper, you should write it up. I'm thinking that it's probably time for us to come up with an assignment. Let's do that because I got the feeling that maybe we haven't done very much in terms of ordering papers. So let's create a new homework assignment. And we'll call this readings. That's a bad name. Papers. Paper list. And save and edit. We'll make it due next week, and it's due at 12, and you probably need a couple or 3 hours for this. We'll display it online, and we'll submit it online, and submit URL no, multiple drafts yes. I beg your pardon? Spring break. Are you sure? Yeah, I guess that's right. So then what we'll do is present, create a PowerPoint presentation that describes the contribution of, I don't know, 10 prior papers that you have read for the course. That's not too many, right? 10 papers, that's nothing. Each paper should take no more than one slide, and it could take less. Maybe there's something to be said for the main points that each paper makes. You could probably do it in 2, maybe 3 bullets, and that's it. And then you're going to have 2 weeks for this, so that's good. Let's see. If you have trouble ordering papers in a timely fashion, just send me an email and let me know, and I'll do my best to expedite things, but I expect you all to be able to use the library properly. Let's see what else we got here. 10 papers that you have read for the course. Each paper should take no more than 1 slide. You can look at some of the prior work that was done under readings courses. It may take time for this to come up. Oh, there it is. So if you look under courseware thesis work, you'll see what others have done. In terms of thesis presentations, you'll see what they've done. So I've got your PowerPoints here, I've got your Word documents. It's very important that we make good progress in creating what's called the historical review. So this is what you're working on now. Why is this paper important to my work? How do I relate my paper or your work to the prior work? So that's actually very good. This is why I read it. I think that probably speaks more to why you're describing the work to us than anything. That should be the key answer that you have to address for any paper. Why is this paper important? Why is it relevant? Yeah, do it. That's a big question you'll want to ask, and then answer. So if it's Raoul, if it's Wetricity, you may find that there are a number of papers already on fractal antennas. I did the search on this, and in fact there are. So you may want to cite some of those. I don't know so much about power and wind turbines, so you have to, you can ask me, but I don't know how much I can tell you. And I know nothing about maglev force fields. Does anybody know anything about this? This may be a totally new field, if you will. If there's never been anything ever on maglev, maybe your stuff is just like prior maglev stuff, except it's not used for transportation on the ground, it's used for transportation in space. So if your application is different, but you're using prior work, that's an inventive leap. Very non-obvious. Not sure about dry ice motors. Dry ice motors exist, right? Somewhat. Are you going to make the first? This can't be just the first dry ice motor ever, can it? Maybe it is. I don't know. I don't know enough about dry ice motors. There are others, right? No? This is the first? Wow, so your stuff is just like liquid nitrogen motors, except there's a difference. We don't have dry ice motors. It's shocking. If your stuff is the first, I think that's very good. There are really no dry ice motors? What about the Stirling engine running on dry ice? Oh, that's not a liquid. Yeah, okay. Air hogs use dry ice. Experiments with dry ice. Somebody has motors. Dry ice blasting for electric motor repair. Dry ice can be used as a working fluid for power on demand engines. No, I don't think so. Here's a science fair project. A Hero engine. You know, the Hero engine just works on steam, right? It spins because steam is coming out, and that dates back to some ancient Greece, right? Like many hundred BC. So what they're doing is they're taking the dry ice, they put it into a sphere, and then because the sphere is warm, the dry ice gasifies, it sublimes, and that emits pressure, and then it spins because it's almost like steam, just vapor. So you've got a dry ice motor that's going to be a, what do they call it? A superconducting motor. Dry ice superconducting motor. Oh, there it is. Compact DIY electric car. Yeah, well, 195K. Yeah, here it is. Getting up to dry ice temperature will lower the cost of using the motor. I don't know if it works. Maybe it doesn't work. Maybe he's, just postulated that it could be done. I don't know if he's reduced it to practice. So in any case, the unique property of your work may make it so that only tangentially related stuff is available. I don't know much about automation for the home, but I have a feeling someone has worked on this. Yeah, so there's probably a lot of work out there. Your stuff may be different, I don't know. How different is the prior work relative to yours? So you can say why it's important, but you should also say why it's not quite the same. Two kind of basic things, I think. Use journal papers. I'd like to say ACM, IEEE, probably others, I'm not sure. Depends on your field. You may be ASME. Some society should have endorsed this, a professional society. Anybody belong to a society other than one of these three? I'm a senior member of the IEEE. Are you a member of another society? Not now? It'd be good if we could get a student chapter here. In fact, if you become a student member of the IEEE, the incremental cost of gaining access to their digital library is quite small. So, in fact, this may help you in this course. And you don't need to get a full year's worth of access to the digital library. For me to do it, it's like $100. But for you guys, I think it's way cheaper. How much is it? $40? Yeah, it's pretty cheap. So, I used to be a student member of the IEEE. Now I pay full freight, which comes to over $200 per year, not including the digital library. But I'm also a senior member of the IEEE because I've been doing it for so long. What else? Due in 2 weeks. Okay? Are we good with this? 2 weeks. Lots of time. Please send me if you need help ordering papers. What else? Here's a sample PhD thesis. I think it's mine. So here's a historical review. That's the same thing as a literature survey. What a historical view does is it cites a bunch of stuff. Here are the different people who took different approaches. Not my approach, but maybe an approach for solving a problem. Other people who organized the literature. In this particular case, my picture didn't come out. I don't know why, but I tried to organize the literature according to a taxonomy. Ah, yeah, here it is. Here's the sensor taxonomy. So in robot vision systems, there's 2D and 3D. In 3D, there's direct range measurement. There's indirect range measurement. For direct range measurement, you have active measurement, which uses either energy from ultrasonics or energy from optics. And then in the optical systems, I think it says here diffraction, static LED, and I don't know what that says. It didn't come out nice. And I forgot. Let's see. What I guess the important thing is that the literature is somehow organized. And probably if you go back, you can find literature cited. And so then there's this big humongous list of all the things that I looked at for the paper. There's a style that you can use for citing things. Some people like to number. I dislike numbers on literature references. I prefer like the name and then a year. That's a style, because then you don't have to worry about numbers being inserted and having them go out of sync with whatever it is you've cited in your narrative. So that's my preference, and you can certainly use it. That's fine. I take the first name, and then if there's more people after, I write et al. That's an abbreviation for a Latin expression, which means et ali, or and others. If there's just one person, I just put in their last name and then the date. That's a reasonable way to go. If there's more than one publication for one person, you might like to letter it. So you could say Whitehead A, B, C, D, E, all in 1990, something like this. I put derivations in the appendix because I don't like to clutter up the narrative with a bunch of equations. How does this Schaefer get cited, right? Let's find him. So there it is. Dempster-Schaefer theory, which is a theory of evidence, was cited with a fraction of one sentence. Another approach to sensor fusion. Dempster-Schaefer, possibility theory, Bayesian approach, uncertainty evolution. Very little was written about each of these things. You can barely tell that I looked at this stuff. Doesn't look like I wrote a lot about it, because I didn't use it. I could have written more, but it wasn't required. But for you, for each paper, you're going to have to at least put in a couple of bullet points. If there's drawbacks to using certain kinds of things, you might want to elaborate. In this particular case, I got a drawback. I thought I'd write more about it. This guy I wrote a little bit more about because it seemed more relevant. So the question of how much you're going to write about something might be, I guess, a judgment call. It's not clear, right? I mean, should you write a sentence? Should you write a paragraph? It really depends how relevant it is. If it's not a very relevant thing, you don't write a lot. If you were going to file a patent on something like this invention, which might be parallel parking with non-holonomic constraints, so that's an automatically parking car. That was my thesis. I could have patented it then, but it was done in 1991, and nobody was using parking cars, automatic parking cars then. It was too far ahead of its time. In the world of invention, being too early is indistinguishable from being wrong. You know, some people have code words for that. They say, oh, the market wasn't ready for it yet. Okay, you were wrong. Just admit it. Don't blame the market. It's not the market's fault they weren't ready for automatically parking cars. Maybe they're still not ready. Here in 2013, they're still not ready. And by the way, had you patented it in 1991, what happened? Well, in 2001, 10 years went by. And by 2011, 20 years went by. And guess what? After 20 years, your patent is worth nothing. Zero. It's a wasted asset. In fact, it's a wasting asset. Because if you couldn't convince the car companies in 20 years to automatically park cars, your patent is not worth nothing. Well, hey, guess what? What about the idea? The idea of patenting the car. Well, if we look at the literature cited, and we look back to, let's say, 1919, whoops, maybe not. There was a patent as long ago as, oh yeah, automatic parking system, 1933. Gee, I guess that didn't take off. How did they do that? They didn't even have computers then. Right? There was no microcontrollers. Automatic parking system, 1933. Indistinguishable from being wrong. Wasted money. Nobody was going to use automatic parking systems in 1933, and I'm here to tell you, they still don't use automatic parking systems. Right? Lexus started to have a product based in automatic parking systems during the life of what might have been a possible patent. Right? But then they gave it up and said, no, nobody wants this. Now maybe later they'll have it, but they still don't have it right now. So unless you guys know different, I don't think you get an automatic. You know, you need braking authority, you need acceleration authority, and you need steering authority, and you have to be willing to give it to the computer inside of your car. I'm barely able to take responsibility for driving my car on my own, especially after a couple or 3 drinks. Right? It's probably not good for me to be driving that way. And the car is probably less competent than I am. So, and then the question is, who's responsible when the car like runs somebody over? That's a big question, because Google has cars that actually drive themselves. Right? And they have a license, right? Google cars have a license in California to drive themselves. How does that make sense? Who do you blame when it hits somebody? Right? When it runs a red light, who gets the ticket? I'm sure Larry, Sergey, and whatever, they can all afford it, but I mean, this is not a very good thing, right? We've been at this for about an hour and a half now, so it's probably time for a break. Shall we take a break? It's kind of warm in here too. Let's do a break. We'll stop this thing.